Hello, welcome to lesson 3.4a on Newton's third law of motion. And essentially the summary of this with the little cartoon here is when you wash a spoon, the spoon washes you back. So first thing we're going to do is we're actually going to just explain a couple of things. First of all, the action force. Now this here is the force that's initiated by object A on object B. Now, if we think back to our thing here, this would be a case of us washing spoon, right? It is the action that we've taken. So this would be your action force. The reaction force is the force exerted by object B on object A. And so this one is exerted. So this is the spoon washing us. Now, I know this meme, or this comic here, this picture, this would be the reaction, is not true in terms of the fact that it's actual forces. It's just kind of funny. But these two forces, so Newton's third law can explain like this. Forces always come in pairs. We have an action and a reaction force. Right? For example, when we push the wall pushes back on us. It can, right? So we say for every action, there is an equal and opposite reaction. So mathematically we could say this, that the force of A onto B is equal negative, opposite, force of B on A. Now this is not on your formula sheet, but that's essentially what it is, right? It's saying here that if A initiates a force onto B, object B initiates a force onto A in an equal magnitude, but in the opposite direction. So let's think about a man jumping off the face of the earth. So the man is jumping up. Okay? The man applies a force down on the earth, right? Pushing the earth down. Man pushes earth down. Now, the earth therefore pushes man up. Okay. Now, that seems all fine and dandy, but remember F is equal to ma, and the man is going to accelerate a lot more because it has a much lower mass than the earth does. When the man is in the air, the man attracts the earth, and the earth attracts the man. When the man lands back onto the earth, the man, again, pushes the earth down. And so the earth will push the man up again. Again, man accelerates more due to a lower mass. And it is a very significantly lower mass than the planet Earth. Okay, we got a video here.
Welcome to the International Space Station. I'm NASA astronaut Mark Vandehei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. We've got a basketball right here. Going to be object 1 on the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So, I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
All right, so let's take a look at this mathematically. We got two boxes. One is 5 kilograms and one is 7 kilograms. So we've got two boxes, 5 kilograms, and they're placed next to each other. So box 5, box 7, this being 5 kilograms, this one being 7 kilograms. A force is being applied to them that causes the boxes to accelerate to the right. So we've got a force going this way, accelerating these 1.5 meters per second squared. All right, what we want to know, if the box B, which we know is this one, has a force of friction of 10 newtons, what is the force exerted by box B onto box A? So this being BA, meaning what force is holding this one back? Well, if we isolate what's happening here on box 7, we've got a force of A onto B, a force of friction equal to 10, we got a force of gravity, and we got a normal force acting in this direction, but these two cancel themselves out because this is moving horizontally. And so these two forces are acting together in order to move this box to accelerate it 1.5 meters per second squared. So what we can say is that the net force is equal to the force of A onto B plus the force of friction. This net force is 7 multiplied by 1.5 is equal to the force A onto B plus negative 10. Now this gets you 10.5 newtons is equal to the force A on B minus 10, or 20.5 newtons is equal to the force A onto B. And it's moving to the right, so that is positive, and that all makes sense, but that's not what the question asked. It said calculate the force of box B onto box A. Well, whatever force A is putting on to B, B is also putting on to A, and that is why it's actually 20.5 newtons equal, but opposite directions, so it's to the left. Thinking about the forces acting on propeller, if we have a plane with a propeller, we'll put some wings on this. Yeah, it's not great, but the air on propeller force actually is going to cause the propeller on the air, and that's going to actually cause the plane to move forward overall. Okay, diagram in your textbook looks like this. And the forces on a rocket and exhaust. Again, in the textbook it looks like this, but really you could just draw it like this, where it's the force of the exhaust on rocket, pushing it forward, and this is the force of the rocket on the exhaust. Okay, if you do have any questions, please let me know. Questions should be found in your unit books.